Secondary overcurrent protection requirements for transformers depend on several factors, including primary voltage, secondary voltage, and primary overcurrent protection levels. The National Electrical Code, or NEC, provides guidelines for determining when secondary overcurrent protection is necessary. Let's examine the two specific scenarios provided, focusing on the relevant NEC regulations. Firstly, consider a 480-volt single-phase primary protected at 125% of the full load amps, supplying a 240/120 volts secondary. In this case, secondary overcurrent protection is indeed required. The primary reason for this requirement is that the secondary voltage is below 600 volts, and the primary protection is not exceeding 150% of the transformer's rated primary current. According to NEC section 450.3, transformers with a primary voltage over 600 volts must have primary and secondary protective devices. The overcurrent protection must comply with the values specified in table 450.3a. For transformers with a primary voltage of 600 volts or less, section 450.3b applies, which is relevant to our scenario. This section mandates that transformers must be protected by an overcurrent device in the primary side, sized according to table 450.3b. If the primary overcurrent protection does not exceed 125% of the transformer's rated primary current, then secondary overcurrent protection is required. Now, let's analyze the second scenario, which involves a 480 volts three-phase primary protected at 125% of the full load amps, with a 120/208 volts secondary. Here, secondary overcurrent protection is not required. This determination hinges on the allowance of up to 125% of the transformer's rated primary current for the primary overcurrent protection. In accordance with NEC section 450.3b, for transformers with primary voltages of 600 volts or less, the primary overcurrent protection is permitted to be set at up to 125% of the transformer's rated primary current, provided that the secondary is also protected. However, an exception exists if the primary overcurrent protection does not exceed the maximum permitted values as outlined in table 450.3b. Secondary protection is not required. Table 450.3b allows for primary overcurrent protection set at up to 125% for transformers with a rated primary current of 9 amps or more. Since the primary protection in this case is at the allowed maximum of 125%, secondary protection is not mandatory. It's crucial to understand the intent behind these rules. Overcurrent protection is designed to protect the transformer from damage due to excessive current flow, which can result from overloads or short circuits. These faults can occur on either the primary or secondary side of the transformer. The NEC provides guidelines to ensure that transformers are adequately protected, while also allowing for practical considerations in overcurrent device selection. When selecting overcurrent protection for transformers, consider the transformer's voltage and current ratings, impedance, and the type of load being served. The overcurrent devices should be carefully coordinated to ensure that they provide adequate protection without nuisance tripping. Remember that the specific requirements for overcurrent protection can vary depending on local codes and regulations. Always consult with a qualified electrical engineer or inspector to ensure that your transformer installations comply with all applicable requirements. Let's delve further into the specifics of NEC section 450.3 to provide a more detailed understanding of the overcurrent protection requirements. NEC section 450.3 deals with transformers over 600 volts, and it specifies that these transformers must have both primary and secondary protective devices. The size of these devices must be in accordance with table 450.3a. This table provides maximum overcurrent protection settings based on the transformer's impedance and whether it has a coordinated system of overcurrent protection. NEC section 450.3b pertains to transformers with a primary voltage of 600 volts or less, which covers the scenarios presented in the question. This section outlines the requirements for primary overcurrent protection and the circumstances under which secondary overcurrent protection is required. According to 450.3b, transformers must be protected by an overcurrent device on the primary side. The size of this overcurrent device must comply with Table 450.3b. This table allows for different maximum overcurrent protection settings depending on the transformer's primary current rating. For example, for transformers with a primary current rating of 9 amps or more, the overcurrent protection can be set at up to 125% of the rated primary current. If the primary overcurrent protection does not exceed the value specified in Table 450.3b, then secondary overcurrent protection is required. However, an exception is made if the primary overcurrent protection is set at the maximum permitted value, in which case secondary protection is not required. This exception is what allows for the elimination of secondary overcurrent protection in the second scenario presented in the question, where the primary protection is at 125% of the full load amps. The rationale behind these rules is to ensure that transformers are adequately protected from overcurrent conditions, while also providing flexibility in the design of electrical systems. The NEC recognizes that secondary overcurrent protection may not be necessary in all cases, especially when the primary protection is set at the maximum permitted value. In such situations, the primary overcurrent device is considered sufficient to protect the transformer from both primary and secondary faults. In addition to NEC section 450.3, other sections of the NEC may also be relevant to transformer overcurrent protection. For example, section 240.21 provides rules for the location of overcurrent protection devices, and section 240.4 provides rules for the protection of conductors. When designing transformer overcurrent protection, it's important to consider all applicable NEC requirements, as well as any local codes or regulations. It's also important to consult with a qualified electrical engineer or inspector to ensure that your installations comply with all applicable requirements. Furthermore, remember that proper overcurrent protection is essential for ensuring the safety and reliability of electrical systems. Overcurrent devices are designed to protect equipment from damage due to excessive current flow, which can result from overloads or short circuits. By providing adequate overcurrent protection, you can prevent costly equipment failures, reduce the risk of electrical fires, and protect personnel from electrical hazards. Now, let's discuss some practical considerations for selecting and installing transformer overcurrent protection. When selecting overcurrent devices, it's important to consider the transformer's voltage and current ratings, impedance, and the type of load being served. The overcurrent devices should be carefully coordinated to ensure that they provide adequate protection without nuisance tripping. For example, if the transformer is serving a motor load, it may be necessary to use time delay fuses or reverse time circuit breakers to prevent nuisance tripping due to motor starting currents. It's also important to consider the interrupting rating of the overcurrent devices. The interrupting rating must be sufficient to safely interrupt the maximum fault current that could occur at the transformer location. In addition to selecting the appropriate overcurrent devices, it's also important to install them correctly. The overcurrent devices should be located as close as possible to the transformer terminals, and they should be properly sized and labeled. It's also important to ensure that the overcurrent devices are accessible for inspection and maintenance. When installing transformer overcurrent protection, always follow the manufacturer's instructions and all applicable codes and regulations. It's also a good idea to consult with a qualified electrician or electrical engineer to ensure that the installation is done correctly. In summary, secondary overcurrent protection is required for transformers under certain conditions, as outlined in NEC section 450.3. Specifically, if the primary voltage is 600 volts or less and the primary overcurrent protection does not exceed the values specified in Table 450.3b, then secondary overcurrent protection is required. However, an exception is made if the primary overcurrent protection is set at the maximum permitted value, in which case secondary protection is not required. When designing transformer overcurrent protection, it's important to consider all applicable NEC requirements, as well as any local codes or regulations. It's also important to consult with a qualified electrical engineer or inspector to ensure that your installations comply with all applicable requirements. And remember that proper overcurrent protection is essential for ensuring the safety and reliability of electrical systems. Let us elaborate on the specific calculations and considerations involved in determining the appropriate overcurrent protection for the two scenarios presented. Firstly, consider the 480 volts single-phase primary protected at 125% full load amps with a 240/120 volt secondary. To determine the primary full load amps, you would need the kilovolt ampere rating of the transformer. Let's assume, for example, that the transformer is rated at 25 kilovolt amps. The primary full load amps would be calculated as follows. Full load amps equals kilovolt amps times 1000 divided by the primary voltage. Therefore, full load amps equals 25 times 1000 divided by 480, which equals 52.8 amps. With the primary protected at 125% of the full load amps, the overcurrent device would be sized at 52.8 amps times 1.25, which equals 65.1 amps. The next standard overcurrent device size would be 70 amps, if using a standard fuse or circuit breaker. Since the secondary voltage is below 600 volts, and the primary protection is at 70 amps, which is greater than 125%, secondary overcurrent protection is required based on NEC 450.3b. The secondary full load amps can be calculated in a similar manner. Full load amps equals kilovolt amps times 1000 divided by the secondary voltage. Using the 240 volt secondary, we get full load amps equals 25 times 1000 divided by 240, which equals 104.17 amps. The secondary overcurrent protection should be sized no greater than 125% of this value, which would be 104.17 amps times 1.25 equals 130.21 amps. The next standard overcurrent device size will be 125 amps. Secondly, consider the 480 volts three-phase primary protected at 125% full load amps with a 120/208 volt secondary. Again, assuming a 25 kilovolt amps transformer, the primary full load amps would be calculated as follows. Full load amps equals kilovolt amps times 1000 divided by the quantity, the square root of 3 times the primary voltage. Therefore, full load amps equals 25 times 1000 divided by the quantity, the square root of 3 times 480, which equals 30.7 amps. The primary overcurrent protection at 125% would be 30.7 amps times 1.25, which equals 37.59 amps. The next standard overcurrent device size would be 40 amps. In this case, because the primary overcurrent protection is set at 125% of the primary full load amps, secondary protection is not required, per exception no. 1 of NEC 450.3b. The secondary full load amps can be calculated as follows. Full load amps equals kilovolt amps times 1000 divided by the quantity, the square root of 3 times the secondary voltage. Therefore, full load amps equals 25 times 1000 divided by the quantity, the square root of 3 times 208, which equals 69.47 amps. Even though the calculated secondary full load amps is 69.47 amps, secondary overcurrent protection is not required in this specific scenario due to the primary protection being set at the maximum allowed 125%. Let's also consider the implications of using different types of overcurrent devices, such as fuses versus circuit breakers. Fuses are one-time devices that melt and interrupt the circuit when an overcurrent condition occurs. They are typically less expensive than circuit breakers, but they must be replaced after each overcurrent event. Circuit breakers, on the other hand, can be reset after an overcurrent event. They are more expensive than fuses, but they offer the convenience of being reusable. When selecting between fuses and circuit breakers, consider the specific application and the frequency of overcurrent events. If overcurrent events are rare, fuses may be a more cost-effective option. However, if overcurrent events are common, circuit breakers may be a better choice. It's also important to consider the time current characteristics of the overcurrent devices. Time current characteristics describe how quickly an overcurrent device will trip or blow in response to different levels of overcurrent. The time current characteristics should be carefully coordinated to ensure that the overcurrent devices provide adequate protection without nuisance tripping. For example, if the transformer is serving a motor load, it may be necessary to use time delay fuses or inverse time circuit breakers to allow for motor starting currents without causing nuisance tripping. In addition to the type of overcurrent device, it's also important to consider the interrupting rating. The interrupting rating is the maximum fault current that the overcurrent device can safely interrupt. The interrupting rating must be sufficient to handle the maximum fault current that could occur at the transformer location. The available fault current can be calculated using fault current calculation methods taking into account the source impedance, transformer impedance, and conductor impedance. If the available fault current exceeds the interrupting rating of the overcurrent device, the device may fail to interrupt the fault, which could result in equipment damage or personal injury. To ensure adequate overcurrent protection, it's important to select overcurrent devices with an interrupting rating that is equal to or greater than the available fault current. Furthermore, it is important to verify the voltage rating of the overcurrent protection device. Overcurrent protection devices, whether fuses or breakers, are designed to operate at or below a specific voltage. Use of overcurrent protection devices beyond their voltage rating is a safety hazard that is not permitted by code.